Welcome to another Light Blade Learning Lab. Today we're going to tackle a subject which has come up just recently when Thinklaser reported back to me on my early videos asking me why I'm so vague on setting up the parameters for cutting, especially as they've provided me with a data sheet which gives me all the cutting parameters for a 60-watt tube, in fact for all sorts of tubes. Now, cutting parameters, in my opinion, is a very inexact science at this moment in time, because there are so many parameters that affect cutting, and any cutting parameter chart that you see only contains the merest hint of all the parameters that could vary and affect your cut. Now, oi mate, can you tell me the way to China? Oh, that way. I think that's a fairly good example of what cutting parameters are. They're just a pointer in the right direction. Let me just show you, for example, some of the things that can affect it. The first and obvious thing that's going to affect your choice of cutting parameters is the material itself. And then you've got the material thickness. And then we've got this one here, which I've called power available for cutting. We've touched on some of this stuff before when we talked about mirrors, when we talked about lenses. The power coming out of the laser may well be 60 watts. It's got to pass through 3 mirrors, which, let's conservatively say, they lose 3% each. And then it's got to pass through a lens, which might be another 3%. So that's 7.2 watts we've lost out of our 60 before we start. So we're down to 53 watts. So we may well have started off with 60 watts, but we're going to finish up with 53 watts. Now that's what I'm talking about, power available. And you won't see anybody talking about power available on any cutting parameter charts. They will talk about what your tube delivers, supposedly, not how your machine is set up. So if your mirrors start to get a bit dirty or your lens gets fogged up, this number here can drop considerably, and it can affect substantially the performance of your cut. Now, the next thing that affects the cut is obviously the cutting speed, which you have got control over. When you look at the Thinklaser website, they do mention different types of lens, but only one of them is specified as a focal length. The other thing that can affect the cutting is, and I'm talking specifically about cutting now and not engraving, is the position of the focal point. Now, you can have the focal point set on the surface of the material, or you can drop the focal point so that it's actually inside the material itself, and that has a significant effect on the cutting performance. And the final thing, depending on whether you're cutting acrylic or whether you're cutting some organic material like leather or wood or MDF, air assist is a very important factor which nobody ever seems to mention much about. When we see a chart which tells us that for a given material and a given thickness, all we need to do is use 60% power and a speed of X, that's only half the story. And that's really what I'm talking about. Now, to establish cutting parameters for your machine, only your machine will have all this set of parameters. This is the most important thing on your machine, which is the power that you're delivering, because that's under your control. I suppose theoretically any supplier of cutting parameters cannot legislate for the quality of your machine, and so consequently they give you best condition. But we don't know the condition of their machine when they set it up. Maybe their machine was similar, maybe it wasn't. We just don't know. So the whole thing about cutting parameters is uncertainty. And so what I'm going to do is to show you how you can generate your own cutting parameters and populate RDWorks with information that is pertinent to you and your machine. Now, ideally, you would like to know what power your machine is delivering, not what power percentage. Percentage is one of the worst things that I can ever imagine for power, but there is no other way of defining power unless you have a power meter, and you generally keep using the power meter, as I do, to check the power of the machine. But that's because I'm purely using this machine to understand and expand my knowledge about this technology. The title of this section is Cutting Parameters Fact or Fiction. I'm sorry, I'm going to be a bit hesitant. There is a small amount of fact in this table, if you can find it, but there's a lot of fiction. Let me point out why I don't use these tables and I use my experience instead. We've got a whole range of laser tubes here. The one that I've got is a 60 watt tube, so let's just focus on the 60 watt. First of all, up in the top right hand corner we can clearly see that it says use 95% laser power. Well, I think we've already established that 95% laser power is a killer. It's not going to do your tube any good at all. On my machine at 67% power, I should be overdriving the tube and seriously shortening its life. That immediately brings into question the validity of all these figures. Because if they were done at 95% power in the factory on a machine which on that particular day produced those numbers, that's fine. That's fact. But they're not fact for your machine or my machine. Cutting parameters are a hugely complex subject which I've tried to stay away from up to now, and there is no way that I can begin to tackle cutting parameters in one session. If I was using a machine all day every day for production, I would focus in on just a few cutting parameters that suited me and my machine and my production. I don't have that luxury. I'm an inveterate fiddler. I like to understand how things work, and as such, when I look at these tables, they are practically meaningless. I keep using disparaging terms about these tables, and now I think I really ought to justify myself by pointing out some of the reasons why I'm being so disparaging. Let's just take this first section here, acrylic. I understand acrylic quite well because I've done a lot of acrylic work. First of all, this table is being in the process, hopefully by the time you get your machine, this table will have been completely revised and a bit more sense put into it, because I've already pointed out a lot of problems to Thinklaser. First of all, when we look down the thicknesses there, 3mm, 3mm, hang on, shouldn't that be 5mm or 6mm or maybe 4mm? But it's certainly not 3mm. We've already pointed out the 95% laser power problem. Okay, let's look across the top column and let's just focus in on my particular 60 watt tube. We've got two columns there, two speeds to choose from. We've got a highest speed and a best speed. Now, what does that actually mean? As an absolute novice, you would come into that and think, well, I can cut that at 20mm a second if I've got a 60 watt tube. Wonder what the best speed is. Why would I go slower? Is it something to do with the surface finish? With acrylic, there are two speeds that you can cut at. One of them is high speed, and you can put high speed with a lot of air, or you can go slower and you can get a better surface finish with using less air. Let's have a quick look at the notes. And sure enough, when we look over at the notes, it says, please pay attention to the airflow. Okay, it's in a bit of Chinglish there, but basically what it's saying is that if you run with low airflow, you get a better finish. So there's a sort of logic when you understand how to cut acrylic, but as a novice, it wouldn't make any sense at all. The machine is supplied with 3 lenses, a 2-inch, a 2.5 and a 4-inch lens. I've added to that collection with a 1.5-inch lens of my own manufacture. What do these figures apply to? Because they don't apply equally to every lens, because the density of the power of each lens and its ability to cut changes. So there's one major piece of information missing from this table, and that's the lens that they used to produce this data. When you're cutting thicker materials, the lens narrows the beam down to something called a focus point. If you're engraving, you need the focus point set to the surface. If you are cutting different thicknesses of material, you need the focal point set to different depths in the material to get the most efficient cut. I'm still trying to find out what KINF is, or KINF. Should that be knife? Just a bad spelling? As far as I can find out, KINF is a Russian oil plant. I've got no clue what that means. Now when it comes to MDF and HDF, with my 60 watt tube, they tell me I can run at 15 or 12 millimeters a second. Now from personal experience, I would never want to run at slower than the fastest speed that I can possibly get out of the machine. You put the power up to its maximum, you put the airflow, as they mentioned at the end here, up to its maximum, and you see just how fast you can run. The faster you can run for the maximum power, the least amount of charring you get on the edge. So why would you want to run at slow speed? It's a puzzle to me. Now this relationship between speed and airflow is a subject that we will tackle in a future session. It's a very important subject and it has significant effects when it comes to cutting. And now we come on to something which is very, very controversial. They tell me that I can cut PVC in this table and they give me the parameters for doing it. Yes, I can cut PVC, but no, I would never cut PVC, and I would advise you to never cut PVC, because in cutting PVC, the chemical reaction caused by heating PVC releases chlorine gas and also hydrogen chlorine gas. When it comes into contact with moisture, will turn into hydrochloric acid. I don't think I want to cover my eyes or my lungs with hydrochloric acid. Thank you very much indeed. And by the way, it will have no good effects on the slideways and the electronics in your machine. Well, I think that's enough critical comment about that table, and one of the reasons why I don't use the table that was supplied with the machine. I must reinforce the fact that I said at the beginning. Thinklaser are no different than any other company. Any parameter table that's supplied lacks information and is only a guide. The fact that this one possesses some dangerous suggestions has been pointed out to Thinklaser, and they are in the process of correcting that. So by the time you get your machine and look at this table, it will probably be unrecognizable. To justify what I'm saying about all cutting parameter tables, I'm going to take you to one of what I consider to be one of the slightly better researched sets of data out there, and that's on a site called Thinklaser. Now they provide you with a set of parameters for these different wattage tubes. They haven't tried to put them all onto one table. They've kept them on separate tables. So we take a look at the parameter table for my particular 60 watt laser. Now these tables are slightly better than the other set of data that we looked at, because first of all they tell me that this is a standard laser head, and so this data applies to a 2-inch lens. And again, we've got just one speed, maximum power, and it says power in corners. Well, I think as far as the setup is concerned, that's max power and min power. We haven't tackled this subject of max and min power for cutting. This is yet another complex subject which we shall deal with in a future session. But at least there's an attempt here to show you that there are two possible powers that you can use. So this table is slightly more informative. Again, we've got thicknesses, and we've got just one speed now, and we've only got one speed for acrylic. There is a catch-all at the top here which covers them to a certain extent, which basically says suggested parameters for some materials. They're not saying these are absolute parameters, suggested parameters. And it says, again, the parameters might be different according to different machines. Now, the other thing that you'll notice about this table is they do mention foam in here, which depends on what sort of material, plastic you're talking about. It could be producing toxic chemicals. Research it very carefully before you do it. I have pointed out in the hazards of materials that you should be very careful with plastics. And when we get down here, they do mention plastics. Oops, we don't suggest you do them. So with a 2-inch lens, they're only giving you information regarding 2.3mm thickness and 2.7mm thickness and 5mm thickness. So they're not really giving you too much information here. These are very much more of an outline guide. They also mention cutting with a 4-inch focal length lens, but they don't mention cutting with what they call their high resolution laser head. Now, their high resolution laser head, I think, but I'm not absolutely certain, I think that basically is a 1.5-inch lens.
Well, here we are back at the machine. I promise I've finished my rant about the dubious nature of the existing cutting parameter charts that are available, not just from Thinklaser, but basically wherever you go. They've all suffered with the same problem: too little information to be of any serious relevance to you to repeatedly set up your machine. I suppose in a strange sort of way, I feel a bit like my mum used to. I always remember my mum being able to just go to the cupboard, take out all the ingredients for a cake, throw them into a bowl, and a cake magically appeared, and it was perfect every time. Now, I don't look at a recipe book, I don't look at cutting parameters. Within 2 years, I have gained a great deal of, I don't know how the word, perhaps the word feel is the right thing to use. I understand how various lenses affect the cutting. I understand how airflow affects the cutting. I understand how speed affects the cutting and power affects the cutting. And I mix all these ingredients together in my head when I've got a problem. And I come up with nearly the right solution most of the time. Now, as a novice, you don't have that skill or that ability. And I don't know whether it's something that's unique to me or whether I'm just plain bloody lazy because I don't want to go through all the work of filling in cutting parameters that I'm just about to demonstrate to you. We're running out of time in this session to actually do any real cutting parameter test work. But I promise you, in the next session, we will spend the whole of the session going through ways in which you should, or methods to approach setting up cutting parameters and filling them into charts. Now, the cutting parameters that I shall be telling you about will be complete. They will be just like a Jamie Oliver recipe. You will be able to follow them, and provided your machine is the same as it was today when you left it yesterday, they will work. And if it doesn't work, it means that there's something wrong with your machine. And that's the great thing about having exact cutting parameters. It keeps an eye on the health of your machine. Now today, we're going to finish off this session by looking at some of the rather key features that you ought to add to the notes when you're doing your parameter setup, because they are very important things that you need to understand, but they're things that nobody ever mentions in any parameter charts that I've ever seen. It all comes down to experience, but experience should be included in your cutting parameter chart. I'll put my glasses on to look a bit more studious, and away we go. Now, how many cutting parameter charts have you ever seen where they mention anything about the extraction? How many parameter charts have you ever seen where they tell you exactly what you should do with your air assist? There are some vague references to it in the Thinklaser charts, but they are vague references. As a novice, you would not understand what they mean. as an experienced person, I can read into them what I think they mean. Right, now what I've got here is some of this card that I used for my focus ramps. And so that I don't waste my time and effort, I'm going to make some more focus ramps. Now I've got 3 sheets here to make 3 focus ramps in 3 different ways. And I'm going to demonstrate some very critical things about the performance of this machine using that piece of cardboard. I've got a 2-inch lens in there. I've got a piece of card here. If I was sitting on the honeycomb bed with the airflow on, there's a possibility, only a possibility, that it will sit flat. But bear in mind what we've just done with focus. It's quite important that you try and make sure that any job that you put on here is flat. Now, as you can see, this cardboard is not flat. And I can turn it over, and the ends are sticking up in the air. Well, to be honest, it's much easier to put the sticky up ends downwards and pull the middle down. You can either put little teeny-weeny pieces of metal along the edge here. So now we've got a flat piece of material. Key issue number 1. Now the first thing I'm going to do is to raise up the table to almost its highest extent so that it's more or less level with the top here. And there's a good reason for doing that, which I'll explain to you shortly. So I've got to set that to 5mm. So what I should do, I will drop that down onto the 5mm step and lock it up. To make sure that my air supply, and I'm going to take this off for a minute so you can hear it, it's running completely flat out. It's off and it's fully on. So I've got full air assist. And the only reason I'm doing that is because you can't really hear it under there. I'm going to turn the extraction system on now. Okay. So we've got plenty of airflow passing through here. It's not as good as it could be because we've blocked off a lot of the flow because of this table here. But what I want to do is demonstrate to you 1 or 2 things. First of all, we've still got good airflow through here, and we've got our air assist on here. I can hear something. I'm sorry, I'm going to have to stop that. I've got the power set to 15% for that engraving. And I'm going to turn the air off a minute. Can you hear how noisy the cut is? Hear it? Now I'm going to stop that. Because I've got the power set to 15%. Now, a completely different subject which I will have to tackle at some future point in time is high frequency impact engraving. It's a very strange characteristic and a very useful characteristic that you get with a laser tube of good quality. You'll hopefully see how clean the engraving is. There's not much smoke damage on there. It is, even though I've got the air assist on, I've got basically quite clean engraving. That's because I've got this noisy type of engraving. Now I'm going to change the power from 15% to 16%. In fact, I'll go to 17% to be sure that I'm clear of this zone. Okay, now for the moment I'm going to leave the air off so that we can hear the difference between this. I'm calling it engraving, but it's not. It's cutting at very low power so that it doesn't actually cut through. It's not proper engraving. You hear how quiet it is? Let's turn some extraction on now.
notice that I'm cutting this straight down onto a piece of steel. And it is giving a slightly hissy effect, which is not the laser beam itself, but it's, I think, a reflection off the steel underneath.
There is a bit of misting on that surface there. These lines look as though they're a little bit brown on either side, but that's where the smoke has actually blown back onto the surface of the lines and made them just like shadowy. But that's not the only problem that we've got with this approach. We have two problems. Number one, we've blown out a huge amount of tar. In other words, the cellulose, when it's cut, produces this tarry residue because it's a wood, it's a resin in there, and it's all sticky on the table. Now that's a major disadvantage in one way, but hey, if it wasn't on the table, it would be in the filter. That's what's not on the back of the product. So this really is not a very satisfactory approach for cutting things. As I said, the only good thing about it is that with a little drop of this, it's on there, not in the filter. And it's not until you see something like that that you realise just how much stuff is going out into the filter. It's even worse with MDF. It's 10 times worse with MDF. And you also get a similar sort of residue, but it's a white, sticky, clear residue or a coloured residue when you cut acrylic. Acrylic produces straight, methyl acrylate solution, which is a horrible white sticky material. Or if it's a coloured acrylate, it's a coloured material.
But now I want to try and solve two problems at once. If we take a look at these, you'll notice that they've got a sort of a bit of a shadow, dusky hue to them. With your air assist, you're actually blowing the smoke back and painting that smoke debris back onto the surface. So the last thing you really want to do is to have your air assist on. First of all, if we turn the air assist off, which I have done now, the problem is that we're likely to smoke the lens. So what we need to do is to make sure that we've got lots of airflow passing across the job so that we don't stand any chance of doing just that. The way that we're going to achieve that is by dropping the table down a bit. The first thing I've done is stop the rubbish from collecting underneath here, so we should finish up with clean surface underneath. And now what we want airflow passing underneath, a small amount, but we want a lot of airflow across the surface. Because the smoke comes up and we don't want to blow it back down again. We want to push it away as quickly as possible. And the way that we're going to achieve that is by going into the Z mode and dropping the table down so that the table sits approximately level with this surface here.
There we go, head's dropped on nicely. And now what I'm going to do, I'm going to move this as close as I can to the front edge of the machine. So here I am within an inch or so of the front of the machine.
On this lid, I have attached some 1/2 inch thick rubber pads. So the door has got a 1/2 inch gap underneath it. And that will allow a jet of air to fly across the top of the job. And I've made sure that that happens because I've got this solid piece of metal in here which has blocked off the air that would normally pass down through the table. So the only way for the air to get through this machine is to get out the back here to those grills that are at the back there. And to do that, it'll fly straight across the top of this job. And there we go, we'll just have to look at it through the window this time. It's unusual for me to run the machine with the cover down, but in this particular instance it's essential.
So I've turned the air assist off, I've set the focus correct, and we've got plenty of airflow zipping through this gap underneath the door. Now I think you can see the smoke being drawn away at quite high speed. Now when we get to proper cutting, there is a moderate chance that we may actually see some flames on top of the work, because the smoke that's coming up, bear in mind, has got a lot of fumes in it. No, we're okay at the moment, we've got no fire. You can see how well we're drawing the fumes away. There we go, flames. We could just stop that. And what we'll do, we'll turn on just the merest amount of air assist. And the way to check that is to take this off and listen for it. There we go, just the merest amount to blow air out of the nozzle. I mean, all this stuff, original stuff, there's no smoking at all. And then let's take a look at the back. Completely clean at the back. And what have we got on the table? Absolutely nothing, because the smoke has been drawn away. So there's something about the setup of the machine that you really need to make a note of if you're doing cardboard, for example. Make sure you cover the bed and you get a linear airflow across your job. Turn off the air assist. We will now reinstall the honeycomb bed, and you can feel or hear, although this has got air passing down through it, it still isn't enough to suck this completely flat. That's because we've got so much air around the outside that we don't have enough differential pressure here to suck this down onto the table. If it was thin paper, there may just about be enough there. Now the problem with this is we're going to be working on this top surface here, and most of our air is going to come in and go down through here. So we're not going to be able to use this honeycomb bed without any air supply. So we're on a loser to start with if we try and do engraving or cutting on a surface like this, which will smoke up. But I will demonstrate that to you anyway. Now, you would automatically think, remember how we produced horrible tarry shapes on the flat metal surface? There is absolutely no reason why we won't produce the same tarry shapes on here, because there is no airflow underneath this table. You might immediately think there is because there's honeycomb under there. But hey, all the air is passing down the outside. We've got no air passing down here at all. And so each one of these little cells is a dead cell. We've got virtually no air movement underneath this piece of metal, underneath this piece of cardboard at all. And even when we cut through it, there will still be very little airflow, because the only airflow that we've got will be passing down through the cut. So there's a pretty fair chance that if we leave it like this, we will still finish up with some tarry marks on the back. But we'll try it and we'll see what happens. It doesn't do it as it comes towards us, it only does it as it moves away from us, you'll notice. So it's something to do with the airflow. That's because the cut, the smoke is coming out the back of the cut. That's what it is. It might look a bit mucky, and it is mucky for several things. First of all, we've got these cuts that have nearly come through, so we mustn't take any notice of those. But what you can take a look at are all these marks along here. Look, every time it crosses over a piece of the honeycomb table, we get a mark. Especially where the table has already been marked up and it burns off the honeycomb back onto this surface. All this debris that's on here is actually burning off back onto the back of the card. So that's another good reason why you'd want to stand your job off of here, so you get plenty of airflow past it as well. Right, so I've done a couple of things now. First of all, we've put some standoffs on there. So we've got air underneath, we've got air across the top, we've got no air assist on. I've wound the let's call it engraving speed up to 180 millimeters a second, and I've put the power up to 18% to try and get rid of this hissy cut. There's a hint of that cut coming back. Can you hear it? And that's even at 18%. See, when the smoke's blowing away from the cut, now what happens is the smoke is coming out the back of the cut towards us and having to draw all the way around the nozzle. Can you see that? Look. Now the smoke is coming this way. Well, in the overall scheme of things, that's probably the best one so far. And we compare that with a sort of a typical example of something that has been done with air assist. You can see the difference here with the air assist, how we've blown the debris back onto the surface, and here we've allowed the debris to come up and be drawn away by the rapid airflow in the machine itself. Now, those are the sort of subtle changes and subtle things that you need to make a note of when you're setting up your parameters. But nobody will be telling you about these in any parameter library that I've seen. So once you get your job right, you'll need to make sure that you note the type of table you're using, whether you're using standoffs, whether or not you've got air assist or not. And somebody's going to say, oh, using no air assist means we could smoke the nozzle, we could smoke the lens. Yes, I agree, there is a possibility of that. So what we'll do, let's just have a look at the lens. I would say there's zero damage to that lens. There's no smoke getting up in there. And why? Well, I think it could be something to do with the power that we were using. The fact that we had a flame there, and the flame means that we were burning the smoke and it was not getting a chance to go back up inside the nozzle. Or, when it wasn't burning, it was being drawn off so quickly that it never had a chance to get back up inside there. Well, thanks very much for persevering with me today. It's been a bit of a grumble session, but I hope in the end we've found out some interesting stuff, and this is a prelude of the sort of way that we should be tackling the next session. We should be doing things that you probably won't see demonstrated elsewhere, but hopefully I should be able to give you some tips on how to quickly get to the best cutting parameters for the job that you want to do. The procedure is the same for each. It's just that you've got to spend a lot of time doing it. And I don't always have that much patience, which is why I just pick them out of the air. Thank you very much for your time, and I'll see you on the next session.